Okay, so these are the problems we didn't quite get to in section for section G. So let me go over this. For students are thinking about grad school, and there are their preferences: Adam, Becker, Christie, and Dan. And four schools are UCLA, Stanford, Harvard, MIT. So we're going to do the two-sided matching to try to get a solution that is somewhat good for the applicants. So first of all, based on this list, we might be asked questions like, is this Pareto efficient? Now, I think Pareto efficient really in our setting here is just asking about, is it Pareto efficient for the student? We're not really looking into Pareto efficiency for the universities because they're on the receiving end of the proposal. So we're kind of asking the question, will the proposal from the student where A applies to L, B applies to S, C applies to H, would that be good matching? Would that be Pareto efficient for the students? So, well, let's try. Well, the key to Pareto efficiency is that, is there any other outcome that can beat it with at least nobody's doing worse and somebody's doing better, right? So that's Pareto efficiency. Now, if A is going to L, B is going to S, C is going to H, and then D is going to M, would that be Pareto efficient? There are many different ways we can show that this is not. For example, we can have A and D swap positions, right? Because they have their least favorite outcome. So if they swap, they should at least do a little bit better, right? So therefore, A will go to M instead, and then D will go to L instead. So both of them are doing better, right? Similarly, we could also have B and C swap. Then B would go to, actually B and C wouldn't swap because B would do worse. So that doesn't work. What about, let's say, A and B swap? Then A would go to S, that's better than L. B would go to L, that's better than S, right? So yeah, that's another possible swap that could potentially change the outcome for the better. So therefore, there are many different ways we can show that this is not a Pareto efficient matching for the students. What about if I want to just use the Gale-Shapley two-sided matching method from the beginning to the end to find a particular solution that is stable? It's worth bearing in mind, this is not the only method. This is just one of perhaps many algorithms that we could potentially arrive at a solution for the two-sided matching. It's not to say that this is the best solution or to say that this is the only way to do this. But this is one very easy to understand and easy to follow steps that we can do for matching two-sided that gives somewhat stable, not somewhat, a stable solution that is somewhat good. So let's take a look how to do that. Well, first of all, we are listing out the potential receivers, which is L, S, H, and M, right? And for the people applying for them, we are going to pick their first favorite outcome and list them underneath. So A is applying to Harvard, B is applying to LA, C is applying to Stanford, and D is applying to Harvard as well, right? So this is their first choice. But unfortunately, they can't all get their first choice, right? That should be D, not H. Then it becomes the school's choice. The schools don't pick their favorite, but rather they eliminate their least favorite candidate. Okay, so we're not settled on the favorite, but we're getting rid of the least favorite. So in round one, D will be eliminated from Harvard. So if D can go Harvard, then where does D go? Well, D will try to go to LA instead. So in the second round, I get both B and D trying to get into LA. And then LA will decide, okay, do I like B better or D better? Well, from LA's perspective, B is preferable to D, so they're gonna eliminate D. And D have to choose again. So now D then goes to its third choice, Stanford. So B, C, D, A. And Stanford goes, okay, between D and C, I'd rather have D, not C, right? So let's get rid of C, and C has to choose in the next round. Then B, D, A, and then where would C go? Well, C's second choice is Harvard. So C would try to get into Harvard. And Harvard again chooses and say, oh, okay, between now A and C, not A and H. A and C, I like A better. So let's get rid of C. In the fifth round, then C goes to, okay, L, then B and C here, D and A here, and L choosing between B and C would choose C, not B, right? So B gets kicked out. Then B goes to M, and that was the game. Right now we have a match between the 4 students and the 4 schools. So Christy will go to UCLA, which is her third choice. Dan will go to Stanford, which is his third choice. A will go to Harvard, which is his first choice, and then B will go to Massachusetts, his second choice. So again, you can see that it's not the best outcome for everybody, but it is a stable outcome. There's no switches that they want to make that will make both of them do better. And you can check that, you know. Okay, so this is the Gale-Shapley method of two-sided matching. Okay, the last is a bit of a bidding game. I played it in the GNI sections, so it's kind of hard for me to show this. But let's say here I have 3 students. There's an item. Let's say I don't know, a Pokemon card or something. Not that rare anyway. So let me use a different color. A think it is worth, let's say, $12.4. And then B think it is worth $14.2 to him. And then C thinks it is worth $17 to him. He really likes the card, while the other 2 didn't need the card or like the card that much. So we'll try to examine the different auction schemes and how that would turn out. So for the English auction, which is the normal kind, you don't need to know like what is English, what is second price, what is Japanese. So it will be, if it is given on the homework or given on the test, it will be explained to you what they are, right? Where the normal kind, where people call out after one bid after the other, who would win roughly, how much would the person pay, what profit? Okay, so that's the question. Assume the bidding starts at $1 and must go up in units of dollars, so no like decimals, right? So therefore, okay, so how do you do this? Let's say B starts to say, okay, $10. Then A goes, okay, 11. C goes 12. Then A will kind of drop out, right? Because A do not want to bid over $12 because once we get to $13, A doesn't think it's worth it, right? And up to $14, B will think it's okay. B will still bet $14, but once B says $14, C will say, okay, $15. Then B will not try to go up again because it's no longer worth that much money to him. So therefore, C will get it at $15 and make a $2 profit, right? So that's the outcome for this very simple bidding scheme. So for the second one, for the second price sealed bid auction, where the highest bidder gets it for the amount the second highest bidder bid, right? So therefore, this is a bit of a gamble. And an interesting question came to me in section I. One person thought about, okay, what if, let's say, just B bids $1, right? Let's say B bids $1, and then C all of a sudden say, okay, I'm gonna bid $100 on this. Then nobody would try to bid higher, right? Nobody would try to bid higher than $100 because if they do, they're gonna pay $100 for it. So they're gonna drop out, and therefore C will get it for $1. I think that is true according to how the game is stated here, but let's modify the game a little because I don't think this is quite realistic because you know, people know you're bluffing, right? So if I'm the auction house, I wouldn't allow this rule to be abused this way. So therefore, I would say, okay, let's modify the game so that A, B, and C don't know how much the other person is bidding, right? So for example, let's say like A will bid like $11, B will bid let's say $13, or maybe let's let B bid a little bit higher, okay? And then C will bid, let's say $17, right? Then C get the highest bid, but he only pays $15 for it because that's what B is willing to pay there, right? So in this case, if they don't know what the other person is bidding, I would say they will only bid slightly, maybe higher than what they try to, what it's worth to you, because they know if they win, they're going to pay a price lower than that. If they don't win, well, then that's somebody else's business, right? So I would say A would try to bid $13, B will try to bid $15, and C will try to bid $17, right? I mean $18. That way, you know, if I win, if B wins, then B will pay the price lower than that, which is 13. B is happy with that. If B loses, in this case, indeed B loses, then it's not my business anymore. Somebody else can get it for $15. I don't care. It's not worth $15 to me, right? So in this case, if they bid it that way, C would win the bid, but he will only pay $15 for it, right? So that's the outcome. C pays $15 and make a $2 profit. I think that's the most logical strategy or thing to do if this is the bidding scheme. Now, for a Japanese auction, where the house calls out 1, 2, 3, 4, 5, and people drop out until there's only one person left, this game will play out essentially like part A, unless people are, you know, so part A, if this is like ABC, they yell out prices themselves, take a jump, right? But for for a reasonable person, they're not going to do any more than $1 bidding increment. Then C, you're forced to do the $1 bidding increment, right? So essentially, we will get to so the house keep raising the dollar amount until everybody drops out. So when would A drop out? A will drop out at $13. B will drop out at $15. And then, so at $15, C will be the only person left. And that's what he pays. So it's the same thing, $15 and $2 profit. Okay. All right. Now, for Dutch auction, where the house starts high, say at $20, this is a wild card and lowers the amount until someone bids, right? So it bidding down. So for this, no clear winner or price. Why is that? Because let's say the house call out $20, nobody would say I want it, right? $19, nobody say I would want it. $18, nobody would say I want it, and $17, nobody would say. Well, C now has incentive to potentially say I want it, right? And if she gets a $17, she gets the item, but she doesn't quite make a profit. So maybe she wants to wait. Let's say at $16, C goes, okay, I'm making a profit now, but maybe I'll wait a little bit longer. Since I do not know how much this is worth to the other people. $15, same thing. $14 now, both C and B will start considering for that to happen, to bid. And again, but they have incentives to try to wait and see, okay, maybe I can make more money. Nobody else is bidding it. And maybe I should wait a little bit longer so I get a better profit on this. So maybe they wait. Okay. So I think in group I yesterday, I think the three groups differed. I don't remember exactly which. I think one group ended on 15, so C gets it for 15 and make a $2 profit. And then I think one of the other group, one person wasn't quite didn't quite understand. So another group bid is like a 17. He actually made a loss. B bid for 17 and made a loss on that. But yeah, but that's that. And then I think a third group went down all the way to like $8. And I think it was B that bid at $8 and made a $6.20 profit or something like that. Yeah. So it's a wild card because you have incentives to wait to try to make a bigger profit. But the lower it goes, the more chances that other people is going to start bidding, and you have higher chance of like losing out to other people and not get the item at all, right? So is it better for me to bid at $16 and make a $1 profit? Or is it better for me to wait till like $10 and potentially make $7 profit? So it depends on what you think it is worth to other people, right? So this is the wild card here. So for the Dutch auction, there'll be no clear winner and no clear price where some people's gonna get it. So therefore, depends on the item. It depends on like how people value these items. Different strategies decided by the house may have slightly different outcomes. It didn't really quite show here, but I think this one potentially that, you know, if people bid just up to their strategy, maybe A just bids 12 and then B bids 14 and then C bids 17, then C could potentially get it at $14 if B wasn't thinking, you know, too strategically about this. So yeah, so there could be differences in the real auction house. Of course, not everyone is so smart and like thinking game theory terms, so it may not be like playing exactly out like this. So okay, all right, cool. So that's the two problems we didn't get to in section G. So hopefully these helps, and see you guys next time.